Okay, so once we have described how to calculate the angular momentum, let's do it for a few cases. Right. So let us find the angular momentum for an object moving in straight line. Okay, so what does that mean? I mean, how do I describe my system? So again, now let us say x, y, z, my coordinates. Let us say origin O, and let's say the particle is moving along x-axis with some velocity v, and at any given instant, its position is at the distance x in that direction. Right. So this is my problem, and now the task is to find out what is the angular momentum of this particle about that origin O. Right. So again, what we need to do is we know that L is R cross. Well, I'll write it MB, but then otherwise below it's R cross P. Right. Now, again, looking at the problem, there could be ways of solving it straightforward in a simpler way, or not just guessing the solution. However, what I'll advise is we always start with this cross product equation and then simply start solving it. Right. Write down things in component form, get the determinant, and get the solution, because that way the solution becomes general. It does not depend on the choice of the particular problem. So if that is the case, then let's first write down what is R. So R for this particle in this system, since it's only moving in x, y, z, it's basically x I cap plus 0 j cap plus 0 k cap. Right? That's a vector R in this case. So I'm going to represent it as x 0 0. So just representing the components of the vectors. Similarly, v vector is vx, right, or rather v. So let me just call this as vx. So vx 0 and 0 because it's only going in that particular direction. R, we know, m the mass is a constant. We can find out what is L. Let's find out what is L. So L is m I cap, j cap, k cap, R, which is x 0 0, vx 0 0. Right? We can get this determinant, and what this gives us is a vector which is a null vector. Right? So of course it's 0. The determinant will be 0, but we are not looking for the determinant value. We are looking for the vector which is described, whose components are described by this determinant. So it's a null vector. Right? And so what it gives us is about this origin O. If the particle is going in one particular direction, then there is no angular momentum. R cross P is 0, right? And it's this is what we have been talking so far, right? In terms of linear motion, this is like a perfect example of rectilinear motion. The particle is going in one particular direction along one dimension. There is no sense of rotation. And that is why, of course, the angular momentum has to be 0. Right? Okay. Now let's change this problem slightly, or look at it from a different perspective. When you say change the problem, let us look at it from a different perspective or from a different point of origin. So let me define this as my origin O prime, right, where this is shifted by some value of, let's call it L. Right? Doesn't matter. So now I'm shifted by origin here. The particle is still moving along this direction, right? So in that sense, when I look from here, at any given instant, now this is the position vector of my particle. It's still moving in the same direction with the same velocity. However, looking from this point, my position vector is now R, which now has both the components, a fixed y component and a variable x component, right? So that is the case when we look at from this thing. So this was, let's say, about O, and now about O prime. About O prime, again, R is x minus L 0. So if this is origin, then this is the negative y axis. minus L 0, and V, we can find out the V by simply differentiating these components, and since L is a constant, we know that this will go to 0, so it's still Vx 0, 0. Right? So the position vector is changed, the velocity has not, because again the origin is simply shifted by a constant amount. So L, let's write it L prime, is then exactly the same way, ijk x minus L 0, Vx 0, 0. And now we calculate it. I cap 0, j cap 0, k cap. Now k cap is minus plus L of Vx. Okay. So when looking from O, the total angular momentum was simply a null vector. Looking from O prime, which is just translated upwards, right? The total angular momentum is well, m is here, so it all will be multiplied by a factor of m. So m L Vx k prime. Right? So just by changing the origin, just by shifting our perspective, now the system seems to have an angular momentum. Right. So one can still say that since the particle is going in the same direction, it's still a rectilinear motion, right? Though we have not changed the state of the system, then where is the rotation? How come we have angular momentum here? And if there is angular momentum, then where is the sense of rotation, right? So for that, we can still look at it on this diagram. We can see how to look at that sense of rotation. So at some time t, the particle is here, its position vector is this. At another time, t prime, at a later time, right, it will move forward. So now its position vector is this one, right? At even later time, the particle is somewhere here. The position vector is this. So what you can say is, it starts like this and the position vector keeps changing direction, right? And that is the sense of rotation. So the position, so although the velocity of the particle is constant in one direction, the position vector is not, as far as the origin O prime is concerned. So the motion is not strictly rectilinear, it's not in one direction now. The direction itself is changing, and that's the sense of rotation of in the system, right? So a perfectly rectilinear motion in one dimension, right, or along one particular coordinate can or will look as a rotational motion, or does have the character of rotational motion, depending on what is my choice of origin, right? And that is why now about O prime, I have this angular momentum L prime, right? Which is then again in the k direction. So since the motion is in x and y coordinate, x and y plane, the angular momentum is in the z coordinate, which again comes from this one. So L, which is r cross p, will always be perpendicular to the vector L, will always be perpendicular to the plane of r and p. Right? And here the plane of r and p is xy, so the angular momentum is in z direction. Right? Okay. Let's take another example to see this in slightly more detail. And we'll take the example of the conical pendulum. Conical pendulum. Let's draw our conical pendulum. Let's say this is. So let us say at any given instant, here is my bob, which is making a circle. This thing is going with angular velocity omega. Okay. Let's describe or define the coordinate axis. So what I do is I do this problem in two different coordinate systems. One is xyz, another is the cylindrical polar or rho phi z. Right? Just to make sure that the equivalence remains. So let's say this is my x. Again, going inside the plane of the board will be by y, right? And I am taking that just because of the choice of drawing this, and the vertical direction is my z coordinate, right? Let me write down this distance from the center of the circle to the object as r. This angle is theta, right? And length of the string or length of the pendulum is L. Right? So this is my conical pendulum, which we have anyway discussed. So we have discussed the dynamics of this. Now we are just looking for the angular momentum for this particular problem. Right? Okay. So from here, what we know, the information that we already have is that R is basically L sin theta. Right? V. So at any point here, since it is going in a circle, the velocity is tangential to the path, right? And if at this instant, let's say if the radial coordinate r points in x direction, then velocity will be simply tangential to that. So in the z direction, but otherwise it will be somewhere in the xy plane. And this velocity is then given as omega cross r. However, so when I write it as v equal to omega cross r, since I am taking this position vector, what basically I am implicitly assuming is that my origin is located at the center of the circle, because then r is the, so let me then write it down as r vector. So then this r vector describes the position vector of the pendulum, right, in this circular path about this origin O. So this is my, okay. So then let's write down about A, because now whenever we are talking of rotational motion and whenever we are going to address problems which requires calculation of angular momentum, we have to know about which reference, about which origin point, right? So let's say about A, V is omega cross R, right? Can we find out V in this case? Yes, because omega is given as, right? Omega is, so it's going around the circle and xy plane, so the omega will be pointing in z direction. Whereas this R in this case is simply xy 0, because the plane of the circle is confined to xy plane. Right? The object is not making an up-down motion there. So we can now find out V. V is I, J, K. So we know what is the V. I just want to write it down in a more general form. Omega and R, xy 0. We can find out what is V in this particular case, and this comes out to be minus omega y I cap plus omega x j cap. So you can do it for yourself and confirm it. Right? What is L? L is R cross M V. We have R, we have V, we can find out what is R cross M V. Right? So let's first find out what is the magnitude of L. So let's write it down as L of A. Magnitude of this we know. So that's a straightforward calculation, MV. And sine of angle between R and B. Right? So not this theta. Not this theta. This is just the angle by which the pendulum is displaced and then makes that conical motion. This is the angle between this radial coordinate and this velocity vector. Now, if it's making a circular motion, we know that this is simply 90 degrees. So sine theta is, or whatever, sine that angle is 1. So this is my magnitude. And what is this magnitude? This is R, this is M, this is V magnitude. V magnitude is omega x square plus y square. And what is x square plus y square? In this case, when the motion is in a circle, the square root of x square plus y square is simply r. So this is m r square omega. That's the angular momentum about this point, right? This is the magnitude. In which direction it points? that we can get when we solve the vector equation. Right? Okay. Okay. Now let's find the magnitude about a different origin. Right? So let's say about this point B. Right? So once we looked at this problem sitting at the center of the circle, now we are sitting at the pivot point. We are sitting somewhere here, right? And we are looking at the same problem. So we are looking basically downwards, looking at the same pendulum moving and trying to calculate what is the angular momentum of this same system, right? So in that case, if that is the origin now, then this is my position vector because it's from the origin to the object. This is my position vector. And now what is the change in position vector from here? So I can write down now r as, well, it has two components, this r and this distance, right, or this coordinate. So this r does not change, so xy, so xi plus y cap, and this additional z coordinate, which is in magnitude L cos theta minus L cos theta, because now this is the origin, so minus L cos theta, and then k cap direction. Right? So this is the new position vector. Velocity vector will not change again, because first either we can simply differentiate it, or we can get it from, to get the actual linear velocity along the direction, and we can do omega cross r. You should try this. If you do omega cross r, v remains exactly same as this v, right? Which was I think I wrote minus I cap omega y plus j cap omega x. Right? So this is the velocity. Okay. Magnitude of v is omega square root of x square plus y square, which is nothing but omega r. Right? Okay. And magnitude of r is this distance. The magnitude of this position vector is simply L, and in that case LB is nothing but L m omega r, right? Or we can also write it as m omega r L. So the magnitude is different, and again here also there will be a sign of angle between this r and this v. However, what you can see is this v is in xy plane. This r will always make an angle of 90 degree with this, right? So it's an out of plane quantity, in plane quantity. The angle is always going to be 90 degree. So that way, again, the sign factor will not be here. It will be simply 1. So this is the magnitude of LB, right? So of course LB is different from LA. This was LA. Is different from LA, and there is a change in quantity. Of course, the dimensions are not going to change. So here also m r square omega, here also m omega r into L. So again, the dimensions of length are at the equivalent level, right? So these are the magnitudes. Now, what about the direction? So let's now do it in a more detailed vector form, and also find out the components. So this is the total magnitude. Now I want to find out the components of these two vectors. So again, let's divide the board into two. So this half will be for about B, and this half will be for about A. So now I'll simply write down L vector as I, J, K, right? R, which was, so now I need to write down R, which was, so M here, X, Y, 0. And here this was, we calculated, so minus Y omega, X omega, 0, right? So these are the components of radius vector, R, and these are the components of velocity, V, which again are same for both the cases. I can solve this, so M, I cap, 0, minus J cap, 0, plus K cap, so X square omega, plus y square omega. This is then m omega x square plus y square k cap, which is nothing but m omega r square in k cap direction, and that is my angular momentum about this point A. M omega r square, so you get the same magnitude, and again we get the exact same vector magnitude also because it's only in one particular direction. So k cap, and where is my k cap? K cap is then this, right? So the angular momentum about this point is have magnitude this, and it points in the z direction. So the motion is in xy plane, the angular momentum is perpendicular to that motion, perpendicular to that plane, so this way. Okay, simple. Next one, what about this one? LB is then same, I cap, j cap, k cap, x, y minus L cos theta, right? And same, y omega plus x omega and 0. Right? Now, the task is for you to solve this determinant. I'll simply write down the solution, right? Which again I can write down from here. So, let us take m common. So, I cap, this is minus xl omega cos theta, where now theta is this angle, plus minus j cap, so j cap will be 0, and so minus, and remains, this is y l, same, omega cos theta, plus k cap, which again will be x square omega plus y square omega. So, although LA had the same magnitude and it only pointed in z direction, LB, of course, we have to check if the magnitude comes out to be same, which it should. Like, doesn't matter, we are doing more explicit calculation, so magnitude should not change. However, here it shows that the direction is not only in the z cap direction. So, when we look from this side, L is not a vector pointing in z direction or x direction or y direction. It's a vector which is defined like this. It has a z component which seems to have the same magnitude as LA. However, it also has I and j. So it also has components along the x and y direction. Right? So that's the important part, that looking from a different origin, the angular momentum not only will change in magnitude, it will also change in its direction. So now the angular momentum, which is only pointing in one direction, has all the three components. Right? And now we can see what are these ij components, and write down individual amplitudes. What you should check is, if you take the magnitude of this, which will be this square plus this square, right? You should still get the same term, m omega r L. So this you can check, and I think we will get that. There is no issue with that, right? So you check that and you get it. Only thing that one has to probably keep in mind as a hint is that r is nothing but L sin theta. Magnitude of this vector is nothing but L sin theta. So you can get one extra term from here. When you take square root square, you will get terms like cos square theta plus sin square theta, which will add up to 1, and then all these quantities can come.